Perfect. Okay, now here's the deal. Before actually giving you the two theorems, the first thing I want to do is get a bit of terminology out of the way and make sure that you all understand what is meant by arc and what is meant by subtended or formed. So here I've got a circle. You can see I've placed the center there. And the setup for many of the questions we're going to be seeing is we start off with 2 points along the circumference. Okay, so I'll say 1 point here and another point here. I'm then going to join those 2 points to the center of the circle. Well, actually, before I do that, just by creating those 2 points on the circumference, what that's done is that it's actually split the circumference of this circle into 2 arcs. Okay, so this down here, what I'm hovering over right now, that's an arc. And above here as well, we have a second arc. Okay, so those 2 points split the circumference into 2 arcs. Now, if I join those 2 points to the center of the circle, yeah, let's try like that. That's not too bad. And like that. Then doing this actually creates what we call 2 angles at the center. One of them is right here, and another one is right here. Okay. Now we say that each of those 2 angles is subtended by an arc. And let me try and use some colors here for you to hopefully picture things properly. This angle at the center is subtended by this arc. Remember, the word subtended just means formed. On the other hand, this angle, this large reflex angle at the center, is subtended or formed by this arc. Okay, and I think everyone's going to be fine with that. That's not particularly, I don't think you'll find that part particularly challenging, but already I like to get that out of the way, because one of the things that's going to be very important in around 1 minute is recognizing that if you're dealing with this arc, then the angle that arc is forming or subtending is this one here. On the other hand, if we're working with this arc, then the angle that's subtended at the center would be this angle right here. Okay. Now, the theorem, the first theorem, and I like to get the nasty one out of the way right off the bat, because most of the others are easier than this one. But the first theorem we need to know, I'll just call it the angle at the center theorem. And center, I'll write it the British way with RE, angle at the center theorem. Okay. Okay, now, here's the deal. There are 3 configurations or setups that can be, thrown your way. All 3 of them refer to exactly the same thing, but they all look rather different. Okay, so I'm going to walk you through all 3 of them. And having these in mind, I promise you could potentially help a lot at the exam, because once you see it, you'll recognize, okay, I'm dealing with the angle at the center. So the first setup is the nice one. Okay, I'll add the center there. And actually, I'll tell you what, I'll keep this circle on my clipboard. Copy. Okay. Now, again, I'm going to add 2 points at the circumference. So I'll add one here and another one here. Okay. I'm then going to join those 2 points to the center of my circle like so. Okay. So at the moment, I've got exactly the same setup as over here. I've created 2 arcs. And of course, because I joined those 2 points to the center of the circle, I've therefore created 2 angles at the center, this one and this one. But now, if I now add another point at the circumference of the circle, say up here, okay, and I join that point to the other 2 points I have, like this. There we go. Then what this does, it creates what we call an angle at the circumference. That's this angle up here. Okay, I'll actually just label that and I'll say that's an angle A. Okay, A is an angle at the circumference, simply because, well, hopefully it's self-explanatory, but because, this angle is actually on the circumference, for lack of a better description. Now, the thing to ask yourself, and this is the very important part, you need to ask yourself which arc on the circle is forming or subtending this angle A. And the answer to that question, hopefully, you can probably tell, but the arc that's forming this angle A is this one at the bottom here, right? I kind of like to think of it as I've got 2 metal rods that are stuck together, and then when I open it up, it creates an arc at the top. that make sense? So the arc that's forming this angle is this one down here. So if I sort of draw over that, that's the arc that's forming that angle. Okay. Now you need to ask yourself, which of the two angles at the center, remember there are two, there's one here and one here, which of the two angles at the center is formed by that same arc? And following what I said earlier on, you should be okay in telling me that, okay, well, the arc that's formed at the angle that's formed at the center by that same arc is this angle right here. Okay, hopefully we all agree with that. This arc is forming this angle at the center. Now, what the angle at the center theorem tells us, and I'll write it out once, what it tells us, and I'll just say theorem, there we go. It tells us that if an angle at the circumference, and an angle at the center are subtended. Remember, that just means formed by the same arc, then the angle at the center, is twice the angle at the circumference. Which is a very long thing to write. There we go. Okay, now what that's actually telling us is the following. When you look at that circle, the thing you need to notice here is, okay, I've got a circle, of course. And what you need to recognize right away is that I have an angle at the circumference and I have an angle at the center. The next thing you have to ask yourself is, okay, which arc is forming the angle at the circumference? We just saw it's this one here. Once you've established that, you need to ask yourself, which angle at the center is being formed by that same arc? And again, that's this one here. Once you've identified those two things, you can go ahead and state, without even thinking really, that the angle at the center has to be 2a. Done. Okay. And I'll immediately, and I'll call this setup 1. And what I'll do is I'll immediately illustrate that with an example. Okay. And so I'll take this guy right here. Okay. So this is this would be a really nice question, by the way, at the IGCSE, if you were given this. Let's say you have to find, well, hopefully it's clear, you have to find this angle A. Now, when you're given this, the thing to notice is, okay, sure, we're given a circle, but you have to ask yourself, what's the information that's given here? Well, first of all, I have an angle, I'm looking for an angle at the circumference, and I'm given one of the two angles at the center. Okay, in this case, it's 150 degrees. The way to solve these problems is to ask yourself, which arc is forming the angle at the circumference? Okay, which arc is forming this angle A? And the answer to that would be, well, hopefully you can see it. Sorry, I'll use a nice color here. Hopefully you can see it. It's this, so that's not big enough, is it? It's this arc right here. It's strange. Why isn't it highlighting nicely? Sorry, I'll use a different color. I'll just use the pen. Hopefully you can see it's this arc right here, which is forming that angle at the circumference. Yeah. Once I've identified that arc, I now ask myself, which angle at the center is that arc forming? And I'm sure you can tell it's this one here, 150. So what this theorem allows us to state is that the angle at the center is twice the angle at the circumference. Okay. In other words, I can quickly just state, all right, well, 150 has to be equal to 2 times A. Solving that quickly by dividing both sides by 2, I now write it, I divide by 2, that leads us to 75, and that's 75 degrees equals to A. In other words, A is equal to 75 degrees. Okay. That's the first one. And I took a lot more time to everyone so that I would write all of this. Okay. Now, I'm going to show you a second configuration for exactly the same theorem, but it's going to look quite different. This one's really nice because it's very recognizable in the sense that the shape that's formed here, the quadrilateral, I find looks a bit like an arrowhead. And so it makes it, when you see it, you recognize it immediately. But let me give you a second configuration. Let's say I had something like this. Let's say I have this. Actually, to save space, I'll write it here. Let's say for a second that I have, again, of course, a circle. And my initial setup will be the same. So I split the circumference into two arcs by placing 2 points at the circumference, and I create two angles at the center, this one and this one. Now, what will this setup look like if I place my third point at the circumference somewhere like here? Okay, well, just as I did before, remember, if I scroll up, what I did is I joined that point at the circumference to the other 2 points on the circumference, which created my angle. And I'll do the same thing here. So I join this point to this point at the circumference and to this one at the circumference. Okay. Now, just looking at that, hopefully you can appreciate right away that that looks quite different. It looks as though we're dealing with a completely different problem altogether. But in fact, we're not. Okay. When you see that, at the circumference here, we do have an angle at the circumference. That's one of the things to recognize here. Right here, this is the angle at the circumference, and I'll go ahead and call that angle A. Okay. Furthermore, we have an angle at the center. Well, of course, we have two angles at the center, this one and this one. And so, in summary there, your reflex has to be, okay, I've got an angle at the circumference and I have an angle at the center. Therefore, I use the angle at the center theorem. Okay, that has to be part of your thinking process. And the way to figure this out is to focus on the angle at the circumference and to ask yourself, which arc is forming that angle at the circumference? Okay, and it's less obvious. It's not the one we're naturally inclined to think of here. The arc that's forming that angle at the circumference is the longer one right here. Okay, and if I sort of draw over it for you to see what I'm referring to here, hopefully you can all appreciate that this is the arc that's forming that angle at the circumference. Yeah, this guy here. So this is the arc. Now that we've established that, you need to ask yourself, okay, well, if that's the arc we're working with here, which is the angle at the center that's formed by the same arc? Well, it's not this one. It's this guy here, right? It's the larger angle at the center that we're dealing with in this case. So the angle at the center that we're working with is this one right here. Okay. Since we have an angle at the circumference and an angle at the center, which are formed or subtended by the same arc, this angle and this angle, we can use this theorem and state that the angle at the center has to be 2a. It's got to be 2 times bigger. Okay. Again, I'll just illustrate this immediately with an example. And that's this example here. Okay, if I take this guy. And this could definitely be asked, right? This could be a 1 or 2 point question at the exam. Setup is, we're given a circle. We need to find this angle at the center, this angle A. And we're given an angle at the circumference. So once more, your reflex has to be, all right, I am given an angle at the center, or rather, I'm dealing with an angle at the center and an angle at the circumference. So immediately you need to be thinking it's the angle at the center theorem. Okay, that's the deal. That's what you have to be thinking about here. Okay, so if you're jotting down some notes, that's one of the things you need to be writing down. It's all about recognizing when to use each theorem. Angle at the center plus angle at the circumference, that means angle at the center theorem. Okay, to use that theorem, the thing you need to ask yourself is, well, first of all, you have to focus on the angle at the circumference. That's this guy here, okay? And you need to ask yourself, which is the arc which is forming that angle at the circumference? And looking at this angle, hopefully you can see that it's this arc right here, okay? That's the arc that we're dealing with. And so if I try and, really illustrate that, we're dealing with, this is the arc that's forming or subtending the angle at the circumference. Okay. Hopefully we're okay with that. Now that you've identified the arc, you need to ask yourself, okay, fine, I know which arc it is. So now, which is the angle at the center, which is subtended or formed by that same arc? And hopefully you can tell it's this guy here. Okay. And so this is quite a common question, by the way. You're being asked to find this angle, but in reality, the way to get there is to focus, or rather, that's a trap, essentially. They're asking to find that angle at the center, and they want you to fall in the trap of, yeah, okay, so that's the angle at the center, this is the angle at the circumference, so this has to be 2 times bigger than that, and that's not the case, though. Okay, you have to stop and ask yourself, which is the angle at the center I'm dealing with? So if I go ahead and call that angle at the center B, okay, then what the angle at the center theorem allows us to state is that this angle B has to be 2 times bigger than the angle at the circumference. In other words, I can go ahead and write that B has to be equal to 2 times 130. That's 130 degrees. B is therefore equal to 260 degrees. Yeah. And now that we know what B is, we can figure out what A is. Remember, angles around a point must add up to 360 degrees. In other words, this angle B plus this angle A has to equal to 360. So I can go ahead and write that. I can say that A plus B has to equal to 360 degrees. But since B is 260, this turns into A plus 260 equals to 360. And I know you have no trouble solving that. I subtract 260 from both sides, leading us to A equals to 100 degrees. Okay, done. Yeah. I'll show you one more configuration. Like I said, there were 3. And like I said as well, don't worry, this is one of the more complicated theorems, but I feel it's important to get this one out of the way because they do like asking questions with this one at the exam. So I'll try it. Let me see. Can I place that here? Yeah, I'll place it up here. Setup 3. Okay. Again, I got my circle. And my starting point's still the same. So I have 2 points at the circumference like this. I've therefore created 2 arcs. And now I'm creating 2 angles at the center by joining those two points at the circumference to the center of the circle. All right, now, going back to my 2 first scenarios, in this first scenario, I placed the 3rd point at the circumference at the top here, or I should say, on the longest of the 2 arcs. In this second scenario, I placed the 3rd point in, on the shortest of the 2 arcs, which made it look very different. But now in this 3rd scenario, I'm going to make it look horrible. Okay. And I'm actually going to place the 3rd point right here. Okay. By doing that, if I now join this 3rd point to the other 2 points at the circumference, I get something looking like this. And you may have seen this, in fact, let me zoom in for a second. You may have seen this scenario in some past papers. Okay. Now, when you look at that, initially, you may think that's not the same problem, but in fact it is. Okay, again, always stop and summarize the information that you have here. Stating the obvious, I have a circle. We're dealing with an angle at the center, right? That's this guy here or this guy here. We'll figure that out in a second. And we're dealing with an angle at the circumference. Okay. And the deal is, if I call this angle at the circumference A, since that's the information we're given, again, I'll say it again. Angle at the center, angle at the circumference. 2 bits of information which tell us that we must be dealing with the angle at the center theorem. Okay, that's what we're dealing with. Consequently, regardless of how horrible this thing may look, you need to stick to the basics. If you have an angle at the center and an angle at the circumference, you use the angle at the center theorem. And the deal is you have to ask yourself, I know I'm repeating myself a lot, you have to ask yourself, which is the arc which forms the angle at the circumference, right? Which arc is forming this guy? And hopefully you can see it's this arc right here. Okay, that's the arc that's forming that angle at circumference. And in fact, as I always do, I'll draw over or underneath that arc. Okay, that's the arc we're dealing with. So now you need to ask yourself, all right, well, if that's the arc, which angle at the center is being formed by the same arc? And hopefully you can tell it's this guy right here. Okay. Consequently, the angle at the center theorem allows us to state that that angle at the center has to be 2 times bigger than the angle at the circumference. In other words, that angle here is 2. Let me zoom in. That's 2a. Yeah. So what you see here, and I'll give you an example, of course, but what you see here is how different the same theorem ends up looking depending upon which of those 3 configurations you're given. Does that make sense? And that's sorry, I'll zoom back in just a second, but that's really important. Okay, it can either look like this, or like this, or like this. And all 3 of those setups refer to the same theorem. Okay, so having a clear visual on that, again, I'll share these notes with you afterwards, but having that clear visual is so important because when you see a circle, you need to be like, yep, I recognize that. That's the angle at the center. Okay.
Are those paper 2 questions or paper 4?
They could, to be honest with you, they could be either.
Okay.
Right. Like if I were the examiner writing a paper 2, I would easily imagine something like this question here. Right. You know, like a 1 or 2 point question. Paper 4, it's going to tend to be much longer, right? And you're going to be dealing with congruent triangles at the same time. And they'll throw in some similarity questions. You know, if you look at the paper 4s, you'll see some of them. Okay. But so to answer your question clearly, it could be either.
Okay. Now, thank you.
No worries. If I now add this guy here, and sorry, I'll try and label these guys. Let me say this is the first scenario. This was the second one. And this is, of course, the third scenario, right? Now, looking at this third scenario, again, you know, I'm going to state the obvious each time. Here we're dealing with a circle. And look at it, you need to be thinking, okay, what's the information I'm given here? You need to find an angle at the circumference, and we're dealing with an angle, sorry, and we're given one of the 2 angles at the center. Remember, please force yourself to, you know, to say there are 2 angles at the center always. And so the challenge here is always to figure out which arc is subtending the angle at the circumference, because that's what's going to tell you which of the 2 angles at the center you are working with. Don't fall in the trap to immediately say, yeah, it's 138. Just like over here, we have to find A. Don't fall in the trap. That's not the angle at the center that you're interested in, because the one we had to use was actually the other one. The way we figured that out, remember, is by focusing on which arc was subtending the angle at the circumference. So going back to this, we need to find A. Angle at the circumference, angle at the center. So angle at the center theorem. Now ask yourself, which is the arc that's subtending, fancy word for forming, the angle at the circumference? And by now, because I've been going on for so long, by now I'm sure you can tell it's this arc here. That's the arc. And so since we're dealing with that arc, now you're in a position to say, okay, the angle at the center I'm dealing with is the angle at the center that's formed by that same arc, which is, of course, in this case, the one we're given. Okay. We can therefore state, using the angle at the center theorem, that this angle at the center must be 2 times bigger than the angle at the circumference. Okay. And so we can go ahead and say, all right, in that case, I can just write 138 degrees is equal to 2 times A. And if you divide both sides of that by 2, 138 divided by 2 would be 69 degrees, and that's equal to A. In other words, A equals to 69 degrees. Okay. Hopefully that helps. That's the first scenario, right? And you guys have to be, well, hopefully you're comfortable in recognizing it. Okay. There we go. Okay. Next one. Remember, if you saw at the very top here, I said the first thing we're dealing with here are angles subtended by the same arc. So this was the first one. Now on to the next one. Okay. And for what it's worth, this one's way easier. Okay. And I'll just say 2 angles
Ça, c'était le plus dur.
Yes, yeah, it's rather subjective, right? To me, yeah. Like I genuinely, when I learned about, I remember learning about this one, and I for a long time, as when I was a student, for whatever, how long it took me, I had a lot of trouble with this one because they all looked so different, right? And I also had trouble figuring out which angle I was dealing with at the center. It bugged me, which is why, like I said at the very beginning, I actually really, when I was a student, I really broke things down this way. And so that's what I did over the last, day or so. I just reminded myself of the way I studied it when I was a student, because I had flashcards, and this is the type of thing I did. Okay, so hopefully that was clear. This next one, though, two angles at the circumference. This one's nice. Two angles at the circumference, subtended by the same arc. Okay, so that should normally, sorry, I'm a bit picky with my notes. There we go. Okay. Now this one should take us like 5 minutes. Okay, if I add my circle here. Here's the deal. I'm going to start again, pretty much always do this. I start by placing 2 points at the circumference. Remember, this therefore creates one arc down here, and it creates another arc up here. Okay, I could, of course, place those 2 points at the side. Makes no difference, but for whatever reason, I'm always placing them down here. And now, leaving these 2 points, if I add a third point somewhere at the circumference, it therefore creates what we said earlier on, an angle at the circumference, right? So I have this angle here, and I'll be creative, and I'll go ahead and call that angle A. Okay. Now, if I now add another angle at the circumference by adding a fourth point to the circumference, right? So if let's add another point right here. And again, I join the 2 initial points I had to that point at the circumference. Then this creates another, didn't mean to erase that. This creates another angle at the circumference here, which I'll call B. And what this theorem tells us, and I won't write it out in words this time because I think that was overkill. It took too long. But what this theorem is telling us is the following: that provided 2 angles at the circumference, so what we have here, right, A and B, provided those 2 angles are subtended by a same arc, which they are here. Hopefully you can tell they're both subtended by this arc. Then those 2 angles are equal. Okay, so in other words, if I just I'll write this: A and B are subtended. But I hate that word so much. Are subtended by the same arc. So they are equal. Period. So A equals to B. Okay, and that's it. Like, that's the theorem. So here the scenario, the way to recognize it basically is, all right, well, what you're dealing with here is you have to recognize that you have 2 angles at the circumference. Fine, that's the scenario here. Then just focus on whether or not those 2 angles are created, formed, or subtended by the same arc, which they are here. Provided that happens, provided they share that same arc, then those 2 angles have to be equal. And it's surprising if you actually take a compass, draw a circle, and do this to scale. I think you'll be surprised. It's obviously true. I'm not making this stuff up. Meaning, if I were to add another angle here, for instance, then that's going to be equal. I could say, I'm going to erase this in a second, but if I had this angle, which I'll call C, that's equal to them as well. And I could even draw one over here. That's going to be equal to them as well. So provided that angle, the angle subtended at the circumference, is formed by the same arc, then they're going to be equal. Okay, which is I quite like that. I think it's kind of cool. And just seriously, if you just doodle on your sheet of paper, you'll see, yeah, it works. I'm not making this up. Now, to sort of illustrate that, let me throw this at you. And this is actually from the worksheet that I shared with you, the notes I shared with you guys. Okay. So here's the deal. You're given this, and you have to find angles A and B. Well, hopefully you can tell, you can tell how to do this because A and B, I mean, sorry, this angle A and this angle 25 degrees, right? Hopefully you can agree that they're both angles at the circumference, first of all, okay? And maybe you can tell, I hope you can, that, sorry. I hope you can, they're both subtended, they're both being subtended or formed by this arc here. Are we okay with that? Both of those angles at circumference are being formed by that arc. Consequently, we can just use the theorem I just told you, and I can say, all right, well, you know, A has to be equal to 25 degrees. Period. Okay. But now to find B, here's another, you know, cool part of this. I'll go back to find B. I'm going to go back to this for a second and highlight the fact that if you're given this setup, then of course A and B have to be equal because they're created by the same arc. But I could say more. If I were to call this angle here C and this angle here D, then, oops, this is meant to be off, sorry. Then can you see that, there we go, that both the angles C and D are also angles at the circumference, and they are also created or formed by the same arc. In this case, it's this guy here. Right, so if I flip, you know, if you sort of look at it upside down for a second, then in fact, yeah, we're dealing with the same scenario again. And so angles C and D, and I'll just add this, and C must be equal to D. Okay, can we all see that it's a two-way thing? And so the same can be said for the circle that I have here, right? I've got this arc at the top, which is creating this angle and this angle. Yeah, are we comfortable with that? Don't hesitate, you know, if that's a bit much, do tell me, okay? Those two angles, A and 25, were formed or subtended by this arc. And so these two angles, B and 45, are formed or subtended by this arc. And so consequently, we can just state, yeah, okay, easy. B equals to 45 degrees. Done. Yeah. That theorem, I find, you know, first of all, it's so recognizable, right? It's far more, I can't jazz it up. Like the previous one, if I go back to it, this guy here, depending upon the scenario you're given, looks so different, right? Between this configuration and the other two, all three of those look so different. This one, on the other hand, I mean, they can't get fancy with it, right? I mean, you have to have an arc, and then I draw these two sort of triangular shapes here and done. You know, they can't get creative with it. So you always recognize that one pretty easily, I find. Okay. Now, I'm going to give you another one. Another guy right here. Let me just think. And I'll just say, okay, angle at the circumference of a semicircle. This one as well, it's going to go faster. This one, it's pretty, I'm writing in French there, circle. There we go. Okay, so here's the deal. Paste, there's my circle. First of all, a circle, oh God, completely losing it. A semicircle is created by drawing a diameter on my circle, right? Now remember, a diameter is, you know, well, actually, I'll be something we haven't actually discussed, at least not at length yet, is if I just add a little circle here, just some terminology in case you weren't aware. If ever this were thrown at you at the exam, I would hate for you to not know it. If I draw a line like that, okay, joining any 2 points of the circumference of a circle, that's called a chord. Okay, I'm pretty sure, you know, we know that, but in case you don't, just know that that's called a chord. And what a diameter is a chord that passes through the center of the circle. Make sense? Hopefully that makes sense. Okay, so I'm not going to dwell on that, just throwing that out there on the side, and now you have that. Now, if I have a diameter, then it creates two semicircles or semicircles. Hopefully you are all comfortable with that. Okay, so it means half a circle. And the idea is if I place a point at the circumference of a semicircle, then its angle, the angle at the circumference created by that point, will always be a right angle. Always. Which I think is pretty cool. Okay, so this will always be a right angle. And it's pretty cool because, I mean, again, you can doodle this a few times to convince yourselves. But if well, that's not what I wanted. If I show you, just quickly draw a couple of these, it really doesn't matter where you place the point at the circumference. The angle it forms will always be a right angle. Always. Okay. And I'll just write that in one sentence. The angle at the circumference of a semicircle is a right angle. Done, period. Okay, that's the theorem. And that one, there aren't 1,000 different questions they can throw at you with this. Sorry, I should have taken a screenshot of it because I've got one that I created the other day. Let me just see if it's open here. Bear with me 1 second, everyone. If I were to quiz you guys, if I were to quiz you guys on this, it's no longer that time, of course, but if I were to, I made a question for myself that I added on the side. I'm just going to find it. Give me 2 seconds. Circle theorems, there it is. Okay. Arc center. Yeah, there it is. Okay. I've got 2 of them here. Yeah. Here we go. Okay, now, if I were to, sorry, I thought I had taken okay. Anyway, I'll give you a quick example. I'll do it here. Example 1. So I draw a circle, place the diameter like this, okay? And I'll draw this. Sorry, to save time, I'm copying what I have on my computer screen here, so I don't want to waste time screenshotting, getting it, and all the rest. So if I just give you this, and I tell you this angle is A, and this angle is 2A. And I want you to find A, of course. Okay, and this, this would be maybe a 2-point question out of paper 2. Okay, this would be my guess. Now, looking at this, what we notice here, or what you should pick up on, is the fact that the segment we have here is a diameter. Okay, that has to be made quite obvious because, well, it's not a guessing game, right? They have to make that obvious. So here, yeah, it passes through the center. Since this is a diameter, we can tell that this point at the circumference is at the circumference of a semicircle, right? This is a semicircle up here. Consequently, we know that this angle at the top must be a right angle, okay? Once we know that, we can use the fact that, yeah, okay, all the angles in a triangle have to add up. They have to add up to 180, right? So in other words, just looking at this, I can tell that, okay, yeah, A plus 2A plus 90 degrees, that's the angle I have at the circumference, have to add up to 180 degrees. In other words, 3A plus 90 has to equal to 180. I subtract 90 from both sides, which leads us to 3A equals to 90. I divide both sides by 3, which leads us to A equals to 30 degrees. Done. Yeah, that's one example of what may be thrown at you. Okay, I have another one here very quickly, and don't worry, we're going to move on after that. Another one that I created here. Oh, I got to get the right one here. Just bear with me, everyone. Give me 2 seconds. Could have sworn I had it. Anyway, I think I remember it. Exercise 2, or example 2, I should say. Again, I'm going to give you a circle. And I have the center here. And if I were to quiz you, I'd definitely give you, like example 1, I'd definitely give you something like that for sure. And I'd also give you something like this one. Let's see if I were to give you, this time I'll draw it like this. Okay. There we go. And I'll say that's A, that's B, that's C. And I'll tell you that AB equals to 13 centimeters. I'll tell you that AC equals to 12 centimeters. And I'll then ask you to find BC. Okay, this is I could easily imagine in, of course, a quiz, but this could definitely be a question in an exam, right? Because hopefully you've already picked up on the fact that I'm testing two skills when I throw this at you. Okay, so looking at this, what we notice is that BA or AB passes through the center, right? It's therefore a diameter. The point C is at the circumference of this circle, and therefore the angle at C is an angle at the circumference of a semicircle. We can therefore use this theorem, and we can state that the angle at C must be a right angle. Okay. Now, hopefully you can tell that what we're actually dealing with here is a right angle triangle, right? I've got this right angle triangle, and it's right angle at C. Because it's a right angle triangle, I can figure out what BC is, what this side length is, using Pythagoras's theorem, right? And if I sort of add the lengths on the diagram here, that's 13. That's the hypotenuse of the triangle. AC is 12. And so I can go ahead and state that the square of the hypotenuse, so that's 13 squared, has to be equal to the sum of the squares of the other two sides. So it's got to be equal to 12 squared plus BC squared. Yeah. But therefore, 13 squared is 169. And 12 squared, well, that's 144. Yeah. And so I can solve this now. I can figure out what BC is. If I subtract 144 from both sides, 169 minus 144 is 25. That's equal to BC squared. And therefore, if I take the square root of 25 has to be equal to BC. And that therefore leads us to BC equals to 5. Okay, and of course, I should technically add the units, but at IGCSE, usually the units are written in the answer box. Okay, so that's that theorem, and I'm aware of the time, so I am trying to go fast, but I do want us to. I'd hate for you guys not to have seen the theorem, so I will carry on. Okay, that's our angle at the circumference of a semicircle. Next one, and this one's pretty neat as well, and the good news is it's surprisingly easy as well. And I'll go ahead and say, all right, the cyclic, quadrilateral. Cyclic quadrilateral, I'll tell you what, I'll just say theorem. I've got to be honest, I don't think anyone actually knows what these theorems are called, by the way. If you look things up, you have one that says theorem 1, 2, 3, and 4. So I'm just giving these names. Okay, this is what I'll refer to as the cyclic quadrilateral theorem. Okay, I'm sure when I was at college in French schools we named them, but I honestly cannot remember what their names were. Now, not important anyway. I've got my circle. And the first thing I feel needs to be defined here is cyclic quadrilateral, which makes things sound incredibly complicated. But in fact, first of all, I think we're all comfortable and we all know what a quadrilateral is, right? A quadrilateral is a polygon with 4 sides. I'm sure we're okay with that. But now if I have a circle like what you see here, and if I add 4 points to its circumference, anywhere, by the way, so I'll add one there, I'll add one there, I'll add one here, and I'll add one here, then if I join those 4 points, in other words, if I create a path joining those 4 points, it creates what we call a cyclic quadrilateral. Okay, so if I join those points, I have this guy, I have this guy, and last but not least, I've got this guy right here. Okay, and I'm going to go ahead and name the interior angles of that cyclic quadrilateral. Okay, so A, B, C, and D. And here's the cool and easy to remember theorem. Opposite interior angles of a cyclic quadrilateral are supplementary. Okay, now supplementary, if you don't know what that means, I will tell you right now. Supplementary means they add up to 180 degrees. Okay, and in fact, I'll make a side note as well. Complementary means add up to 90 degrees. Okay, just so you know, so two different terms there. Supplementary means they add up to 180 degrees. So back to our cyclic quadrilateral here, what that theorem actually means is, okay, well, therefore, you know, if I take any interior angle of a cyclic quadrilateral, it is, sorry, yeah, that's fine. It's supplementary to its opposite angle. So A plus C have to add up to 180, or B plus D have to add up to 180, okay, period. That's the theorem. Okay, so here I can say, all right, well, therefore, you know, A plus C has to equal to 180 degrees. And B plus D has to add up to 180 degrees. Yeah. Now, I think I've got a question on this guy. I'm pretty sure I do, actually. I can already see some. Yeah, let's throw, okay, I'll tell you what, let's throw in a challenging one. Okay, this guy here. Okay, now this one, of course, could be asked at the IGCSE exam, otherwise I wouldn't be giving it to you. But looking at this, we have to find all the unknown angles, and we have three here. We have A, B, and C. Okay, now when you first look at this, there, you know, first of all, there are several things going on, as I'm sure you can tell. Not only do we have a cyclic quadrilateral, hopefully you can see that. I have a cyclic quadrilateral here, right? But I also have an angle at the center here. Yeah. So that's really important. You know, when you're given a question, you need to summarize, you need to take a few seconds to really just stop and go, okay, what's the information I have here? Okay, what am I actually dealing with? Because once you've identified those things, once you've identified what you're dealing with, you're going to quickly identify which of the theorems you use. Okay. So what I'll do is, what I always do actually, I really, and I know I've said this in class, I like to break things up into simpler problems, okay? And I like to get a clear visual on things. When I look at that, the first thing I notice is a cyclic quadrilateral. So I'm gonna start by drawing that, like literally on its own without anything else. I don't want the clutter on it. I want my mind to be as clear as can be to solve this problem. So when I look at this, and I'll just add that angle B and that angle C, okay? Now, what the cyclic quadrilateral theorem allows me to state, just looking at that, my quick sketch I made, I know that B plus C has to equal to 180 degrees. Okay, I think we're all comfortable with that. But therefore, you know, stating the obvious here, I don't know what B is, nor do I know what C is. So I can't figure that out immediately. The ticket, therefore, or the way out of this is therefore to focus on the angle at the center. Okay. And there are two ways of drawing it. There are two approaches. Okay, I think in this case, what I would actually do is, you know, you need to figure out which of the two angles, B or C, you can work out easily. But just look at it, hopefully you can tell, well, you know, the angles around a point have to add up to 360, right? So 230 plus A has to equal to 360. So I would write that on the side here. So I know that A plus 230 has to equal to 360. Okay, therefore A, so if I subtract 230 from each side, of course, right? Therefore A has to be equal to 130 degrees. Yeah, done. So already it's getting better. Now that I've done that, now that I have that, I basically now have both of the angles at the center of the circle. And what I'll do now, if I add another one, draw a new circle. Okay, if I now, I'll sketch, you know, the arrowhead. Hopefully I'm making sense when I say that. I'm going to sketch the arrowhead scenario for my angle at the center and angle at circumference. I should say, if you're more comfortable with this one here, this quadrilateral, right, that would correspond to the second configuration I showed you at the very beginning, and you can work with that one as well. Okay, it doesn't matter which one you go for. But personally, when I see the arrowhead, that's my comfort zone. I'm thinking, yeah, I can deal with that. So if I now sketch that arrowhead scenario, right? So I've got this, something looking vaguely like this here. Whoa, there we go. Okay, that's my arrowhead scenario. And in this case, I've got B here, yeah. And I have both of the angles at the center now. So I'll label them. That's 130 degrees. That's what we just found. And this one, of course, is 230 degrees. Okay. Now to find the angle at the circumference, this guy here, this B. Again, going way back to the first theorem we saw, you have to ask yourself, which is the arc that's subtending the angle at the circumference, right? Remember, that's always the way to use this specific theorem. Ask yourself which arc is subtending the angle at the circumference. And I'm sure you're quite comfortable in seeing that the angle that's subtending B is, sorry, the arc that's subtending B is this guy right here, okay? Consequently, consequently, I can now figure out which angle at the center I have to use, right? And it's the angle at the center which is being subtended by that same arc. It's therefore this guy right here. Yeah. So the angle at the center I have to use here is 130 degrees. And I can state that the angle at center, 130 degrees, is 2 times bigger than B, the angle at the circumference. In other words, I can go ahead and write, okay, well, 130 has to be equal to 2B. Okay. Now, if I divide both sides of that by 2, 130 divided by 2, well, that's 65 degrees. And that's equal to B. So B is equal to 65 degrees. Yeah. Finally, we can actually use our cyclic quadrilateral theorem and figure out what C is, right? I go back to this guy. I now know that B, following what we just found, B is 65 degrees. But since B plus C has to equal to 180, I can go back to this. I can go back to this now and state that, oops, sorry, white, there we go. I can go back to this now and say that 65 degrees plus C has to be equal to 180 degrees. And now if I subtract 65 from both sides, C is equal to 180 minus 65, which is 115 degrees. Done. We have A, we have B, we have C. Okay, now again, that could definitely be an exam question. Like I can easily imagine that happening. Okay, we're nearly there, everyone. Okay, I know this is long, but let's get it, my plan is let's get this done, all right? We've now seen cyclic quadrilaterals. The next theorems all involved tangents. Okay, like I said at the very beginning, I've broken this up into sort of categories, if you wish. Now we're looking at tangents. Okay, so if I just write that here, we're going to be dealing with tangents. And if you've looked at past papers, then this pops up quite a bit. And I'll erase this in just a second. But so for instance, the scenario that I'm sure you've seen with like 2 tangents like this, that's what we're dealing with now. Okay, and then they throw in stuff like this, and you have a triangle and all the rest. That's this stuff. Okay, so if I delete that, done. Now tangents, first of all, let's spend just a second to define what a tangent is. Okay, and don't worry, not particularly difficult, but it does need to be defined. Now a tangent to a circle is a straight line which touches the circle in one point. It doesn't cross the circle. That's quite an important bit of terminology there. Okay, the tangent touches the circle at one single point, okay, hence the fact that it doesn't cross it, it just touches it. And a really neat theorem, first of all, I'll just go ahead and state it, is that the tangent to a circle, let me make that look a little better. I want it to be very painfully obvious here. The tangent at a circle, I can't speak anymore. I'm speaking for a long time. The tangent at a circle will always meet the radius at a right angle. Always, no exceptions. Okay. So if you're given a tangent to a circle, it has to meet the radius at a right angle. Okay, so let me just write that. The tangent to a circle is, or forms, I'll say, forms a right angle, with the radius at the, I'll just say point of contact, okay? Point of contact at the circumference. Yeah, does that make sense? Hopefully. Okay, pretty easy theorem, right? I find that one, well, there's not much to do really, right? You just told, okay, that's the rule, take it. Okay, now I think, again, I'm pretty sure I've got at least one question involving that. Let me just find it. Yeah, I got this one here, don't I? Let me just add that. Okay, so here's a question involving this, this particular theorem. Okay, so here, what are we dealing with? We have to find, we have to find this angle C and this angle D. Okay, now just looking at this, the key thing to pick up on here is, well, let's see, that hopefully you're comfortable, you're comfortable in seeing that we're dealing with a tangent here, right? So that's one thing, already making a mental note, or even if this were an exam, I'd say, yeah, okay, let's add this right angle right there. That way it's clear, I know what I'm dealing with. Second thing though is, and this happens a lot, so I'm going to say it and then it's going to become obvious. The triangle that you see here that I'm hovering over right now, that's an isosceles triangle, okay? Because OB and OA are both formed with the radius of the circle, right? So OB has to be equal to OA. Yep. But a quick reminder, quick reminder, if you have an isosceles triangle, where shall I do this? I'll do this underneath, sorry, I'll do it here. Let's say this is an isosceles triangle. Okay, I'll just write on the side here, isosceles triangle. Okay, now it's isosceles if two of the side lengths are equal, right? And if that's the case, then both of these interior angles have to be equal as well. Okay, so if I call that angle A, that's angle B, then angle A equals to angle B. That's really rather important. We tend to always think of the side lengths, but really remember as well that for an isosceles triangle, the two angles, the two angles that aren't in between the two equal side lengths are equal. Okay, so A equals B. I'm saying this because going back to my triangle over here, hopefully you can tell that that allows me to state that this angle here has to be 27 degrees. Yeah, so it's quite an important rule. I know I've definitely mentioned that before, but I'm just getting it out of the way again today. So if that's 27 degrees, right, then now I'm sure you can see it. This angle D plus the 27 has to, have to add up to 90 degrees. Yeah, because can you see that OBP, this angle I'm kind of trying to hover over right now, that has to be 90 degrees. Okay, so I can go ahead and say, all right, well, I know that OBP, why I wrote F, I have no idea. OBP equals to 90 degrees, right? So D plus 27 equals to 90 degrees. And consequently, D has to be equal to 90 degrees minus 27 degrees. Therefore, D is equal to 63 degrees. Okay, I think we're okay with that. That's the rule I just gave you for the tangent used. Now let's quickly find angle C. Well, since I know that this angle here is 27, and I know that the sum of the interior angles of a triangle is 180, I can quickly say that C plus 27 plus 27 has to equal to 180. In other words, C plus 54 has to equal to 180. I subtract 54 from both sides. Minus 54 minus 54, and therefore C is equal to what would that be? 126 degrees. Okay, nearly there. One next one, very nearly there. Okay, now if I add another circle, all right. here's one that pops up quite a bit. Okay, so here's the deal. If I draw, I'm going to draw two tangents to this circle. Okay, so here it is. I'll draw one like this. Okay, and I'll draw another one. So I'm going to move that a tad in a second. Yeah, there we go. Another one like that. Okay, we're all okay with that. I'll go ahead and I'm going to name a few of these points here. I'll go ahead and call that point of contact A. I'll call this one B. So that's A, that's B, and I'll say that's C. Okay. Now here's the idea. If two, and I'll just state it. If two tangents meet at a point outside the circle, which is the case here, right? When I say they meet, I could have written intersect, right? This tangent and the other tangent intersect at a point C, then they are equal. Sorry, I mean, I could make a longer sentence there. I just don't, I don't want to, and I don't think you want to hear a longer sentence right now. But they are equal. What I mean there is that this length here, AC, has to be equal to BC. Okay. In other words, point C is what we say, it's equidistant from A as it is to B. Okay, so here AC has to equal to AB. Yep, we're okay with that. So in fact, I could add, this little symbol there to indicate that those two lengths are equal. Okay. Now, if I go ahead and throw in a question here, I'm pretty sure I have some because they like this one a lot. And I'll tell you what, I have no idea which one is which. I'll just take this guy here. Let's try this one. Okay. And in this case, I mean, you can tell we're dealing with a circle, and hopefully you can tell as well that I have two tangents, both of which are leaving the same point P. Okay, so right off the bat, when you see that diagram, you need to be thinking, okay, well, the side lengths AP and BP are equal in length, right? So if I were sitting this in the exam, I'd be thinking, okay, I'm not actually asked to find a length here. I need to find that angle at the center, that angle A, as I'm sure you can tell, right? So how would I do that, right? And these questions, again, I'm sure if you've worked through past papers, and by the way, I've got two more past papers for you guys I'm going to share with you. If you have worked through some, I'm sure you've seen questions that at least look a bit like this before. Now, looking at this, I need to find this angle A. And there are a couple of things worth pointing out, okay? First of all, because PBA is an isosceles triangle, this angle and this angle must be equal. Hopefully we're okay with that. And I'll go ahead and call that angle, I'll be super creative again, and I'll call that angle, I'll just call it X. Okay, I've got 2 times the same angle there. Since I know that this angle at the top here is 68 degrees, and I know that the sum of these 3 angles has to be 180, I can go ahead and write that X plus 68 has to be equal to 180. Okay. In other words, 2x plus 68 equals to 180. I subtract 68 from both, sorry, didn't mean equal. I subtract 68 from both sides, which leads us to 2x equals to 112. Okay. Now, if I divide both sides by 2, I have x equals to 56 degrees. Done. Okay. Now notice that I was able to find that angle thanks to the theorem I just gave you, this tangent theorem, right? The 2 tangents are equal in length. That's what told me that this was an isosceles triangle, and that's what in turn allowed me to state that these 2 angles had to be equal. Yeah. And so now that I know that, the next thing I notice is, or the trick really is, how are you going to get from that to this triangle in the middle here? And that's where well, that's where the first theorem I gave you on tangents comes in, because this angle here has to be a right angle. Remember, tangents, a tangent is at a right angle to the radius at the point of contact. That's the theorem I wrote up here, right? That's this guy here. Okay, so that doesn't change. It doesn't matter that you have two tangents. That's always going to be true. So this angle right here, this guy here, has to be a right angle. Okay. But since that's a right angle, of course, so is this guy. Okay, so again, let me give this interior angle here a name. If I can figure out that angle, which is the same as this one, I'll call it y. If I can figure out what y has to be, then I'll be able to figure out what a is. Yeah. And so let's do that. I know that x, actually I'll do it on the side here. I know that x plus y has to be equal to 90 degrees, right? But since x equals to 56, that's 56 plus y equals to 90 degrees. So I subtract 56 from both sides of that equation, and that leads to y equals to, well, 90 minus 56, what's that? That's 34, right? So 34 degrees. Okay. Now that I know what y is, I use the fact that y plus a has to equal to 180. So I'll do that here. Y plus a has to be equal to 180. But since y is 34, that's 34 plus a equals to 180. So that's 68 plus a equals to 180. In other words, I'm sorry, if I subtract 68 from both sides, right? In other words, a has to be equal to 112. Done. Okay. We're nearly there. I know this is long. Okay. One more theorem to throw your way. Then I'll let you be, and please practice these. Okay. Please practice these. Last theorem, again, involving tangents. And this one is the alternate segment theorem. Okay. Oh, anyway. So if I draw a circle, okay, and I'm going to draw a tangent to that circle, something like this. Yep. And the next thing I'm going to do, I'll do is, let me just quickly, I want to make sure I illustrate it nicely. So I will just quickly look at my notes on my computer here. Yeah, there we go. Next thing I'll do is, from this point of contact with the tangent, I'll create sort of a triangle inside that circle, okay, like this. There we go. Okay. Now, the ultimate segment theorem tells us that the angle, make it really obvious, I'll do it big. This angle here, okay, which I'll call A, is equal to this angle here. Okay. So in other words, what we're dealing with here is the angle. This angle here is between the tangent and this chord A. Yeah, that's what we have here. So the angle between the tangent and the chord, we say, I'll actually just read it out, is equal to the angle in the alternate segment, this angle here. Now, we're not going to prove that. You don't need to know how to prove that. But put simply, if I draw a circle, any circle, and if I draw a tangent to that circle, and then from that point of contact, I create anything looking like this. I could draw this. Anything looking like that. Then this angle will always be equal to this angle. Always. Okay. If we had more time, I'd prove it to you, right? If we were doing this in a classroom context, I would prove that result to you. Unfortunately, that's not feasible right now. So what I'll do is I'll show you how that's actually used with an example, okay? And then we're done, everyone. Then then we're home safe. Yeah, let me take, yeah, that's it. I'll take that one there. Awesome. Okay, so I'll grab this. Okay, now looking at this, this is a type of scenario that you could potentially be given. Okay, so clearly, given a circle, we have a tangent, and from the point of contact, they've drawn a triangle inside. Now, this is a nice case because on top of just drawing a triangle, in the two triangles I gave you here, this side length in the triangle wasn't parallel to the tangent. Here it is, right? That's indicated by these arrows on the tangent and on this line, okay? If ever you see that, it means that those two lines are parallel, all right? And look at this without, what's cool about this theorem is without even thinking, we can just state, okay, well, if that's, what I'm dealing with here is, I mean, literally my mind thinks of it as I see tangent, I see point of contact and triangle drawn from that point of contact. To be honest, I mean, really, that's how my brain processes this. So it's rather, simple-minded, my way of thinking of it. I just literally see a tangent and a triangle drawn from that tangent. Fine. Once that's established, I know that this angle has to be equal to the angle made between the tangent and this chord. Okay, so I can just look at this and say that, okay, well, without even thinking, I equals to 53 degrees. Period. Done. Okay. And now since this line is parallel to this one, okay, this angle J has to be equal to this angle. Okay. Now, if I take that away from the circle for a second, what I'm using there is, that's always going to be the case, right? If I have two parallel lines, and if I draw, I'll say that's parallel to that. If I draw a line, any line passing through them, well, this angle will be equal to this angle. We're okay with that? And it's also going to be equal to that angle. And this one will be equal to that angle. Are we okay with that? I think hopefully, can you see that that's exactly what I'm dealing with here, right? So this angle here, technically this 53-degree angle would be this guy here. And therefore this angle here would be this guy here. And this works out nicely because these are parallel, okay? So the alternate segment theorem allows me to quickly state that I has to be equal to 53 degrees. But on top of that, because this line is parallel to this one, it allows me to state that J must also be equal. J must also be equal to 53 degrees, okay? Finally, to find this unknown angle K, I can simply state that the sum of the interior angles of this triangle have to add up to 180. So I plus J plus K has to equal, to 180. In other words, 53 degrees plus 53 degrees plus K has to equal to 180. Finally, if I add these two together, 53 plus 53, well, that's 106. So 106 degrees plus K equals to 180. In other words, K is equal to 180 minus 106. So K is equal to, I cannot think to save my life anymore, is equal to 74 degrees. Done. Okay. That's it. We've seen all 7 of the circle theorems that you need to be familiar with. Okay. Hopefully that helps. The idea here, everyone, more than anything else, is to be exposed to these a couple of times. My advice, I'm going to send you these notes. Okay, I'm going to share these with you. I'll do it I'll probably post it as a message on ManageBack, but I may actually just create a Google folder where I'll throw some things in. Okay. Hopefully this was helpful. Okay, everyone. I'll let you guys go. I know that was long. Okay, so well done for those of you who stayed for the whole period. Hopefully that was helpful for you guys. Okay, everyone.
Yeah.
Cool.
Merci.
Oh,
No
sure.
worries.
Au revoir.
Thank you
Thank
so
you.
much.
Yeah, question.
Une question. Similarities, ça appear beaucoup dans les examens ou pas?
Similarity, yeah, that can definitely pop up. Absolutely.
Mais
Absolutely.
vous l'avez fait samedi, ça, non? Ou vous l'avez pas fait encore?
No, similarity, we did a fair share in class, not as much as I would have liked to. Okay,
Mm.
so if ever we throw in another one of these, I will definitely, one last revision session. I would definitely be looking into, doing one with similar shapes, in particular, similar shapes, similar areas and volumes. Okay,
Ok.
'cause they do pop up a lot. So if we do one last session, that's what it's going to be on.
Ok.
Okay.
Merci, au revoir.
Tomorrow, are we doing what's it called? Volume, area.
I'm up for it. I mean, I'll happily do it tomorrow. That's not a problem for me. I'll send you guys I don't want it to be overwhelming. Okay. But although I know this is a lot, but I'm just being very, very, very objective here in the sense that I feel that, yeah, if we have something to get done, let's get it done. Okay. Let's just power through it. And, sessions like the one we just did, I hope, are productive. So yeah, I'll say yes. And I'll send you guys a link for tomorrow.
Okay.
Okay.
Thank you.
All
Take
right.
care, everyone.
Goodbye.
Au revoir.
Thank you, sir. Goodbye.
Take care.